Hello, everybody. I hope you had a nice weekend. Um, Today, we're going to continue and finish Chapter 4, and we're going to finish it by going over Section 4.4. In Section 4.4, we don't really prove anything. There are things you can prove about the things we're going to discuss. It's more of just an examples section, and we're going to go over some fundamental definitions for the future of studying algebra in particular, if you're interested in pursuing mathematics at a higher level. These definitions appear all the time in almost every topic, every subject in higher mathematics, so it's important to know them. They're all sort of related to a group and sort of generalize the notion of a group, but the way in which they generalize it is slightly different. So the first one weakens the notion of a group to a semigroup. So a semigroup is a set S. The set S corresponds to set G that we talked about for a group. It also has a multiplication, so groups have multiplications, semigroups also have multiplications. And semigroups are like groups except they're missing a few of the axioms. So the two axioms that we still want our multiplication to satisfy are that when I multiply two things in my semigroup, I'm still part of the semigroup. And it has this associativity property. So this allows us to take products, powers for instance, right? If I take x times x times x, it doesn't matter whether I multiply these two x's first and then this one, or these two x's first and then this one. So taking powers doesn't change the structure. This is what associativity allows us to do. So what are some examples of semigroups? Well, the set of integers with multiplication is a semigroup. Now the set of integers with addition is a group, but when you use multiplication, it's only a semigroup. And this is because it has an identity element. So it has an identity element under multiplication, which is just the number 1, but no inverses in general. The only elements with an inverse in Z are 1 and minus 1. 1 is its own inverse, and minus 1 is also its own inverse. The rest of the elements all need to go to the rational numbers to find their inverses. And 0 doesn't have an inverse in any of the things that Z sits inside. You can never divide by 0 is the rule here. So that's our first example of a semigroup. What's another example of a semigroup? M of n, which is a set of n by n real matrices. Is a semigroup under multiplication. Right, and it's very similar to the integers, except it's not abelian, right? We don't necessarily need things to commute. I mean, there are abelian semigroups. This is an abelian semigroup. This is a non-abelian one. Let's do one more. So let K and L belong to Z. And define A subset of Z by A is a set of things is a set of numbers in Z such that which satisfy K divides M and L divides M. So A is a semigroup under multiplication. So for instance, if K equals 2 and L equals 3, then A is a set of all numbers 2 to the m, 3 to the n, such that m and n are at least 1. And I guess it should be plus or minus. So this is a set. It's a set of all common multiples of 2 and 3. And it is a semigroup. Because if I multiply two of these things together using the exponent rules, the exponents here add, and they'll still be at least 1. If I add two things that are at least 1, they're still at least 1. So these two semigroups have multiplicative identities, right? This one has an identity element as 1. This one's identity element is the identity matrix, the n by n identity matrix, but this semigroups does not have an identity element because 1 is not part of A. So not every semigroup needs to have an identity. What's the last example of a semigroup that I want to discuss? Well, what's the group that we've been talking the most about? It's the set of bijections from a set to itself. Which we called S of x. So let's call f of x denote the set of functions any function, not necessarily a bijection, from x to itself. Then f of x is a semigroup. Right, because under composition. If I take two functions and I compose them, I still have a function from x to x, right? Because if I have two functions f and g, and I compose them, then the composition g of f is still a function from x to x. And this associativity rule is very easy to check for compositions. Right, if I have a third function h, it doesn't matter if I compose this one and then h, or I compose this one here, and then g of, this is, which one do I apply first? I apply g first, and then h. Right, so under this big composition, these arrows on the above and below both represent h. I apply f first, then g, then h. F first, then g, then h. right, so it doesn't matter if I do it like this. And I grouped it wrong there, sorry. This is h of g of f. And this is h of g of f. So associativity holds. It's probably something I didn't need to go into quite as much detail about, but associativity holds for composition. So this thing is a semigroup. Semigroups don't have a lot of the nice properties that groups have. So the biggest thing is about solvability of equations. So sometimes equations will never be solvable, right? If I know that g h equals k in a group, this will always imply that h is equal to g inverse k, right? If I wanted to solve for h. But in the semigroup, this is much more complicated. It's not quite as simple. So for instance, if you know that g times 0 is equal to 0 in Z, how do you find what G is? G could in fact be anything. Since 0 is not invertible. Right, if this were an equation in a group, then I would just multiply by this element's inverse on the right of this side of this equation and get that G is equal to 0 times 0 inverse. And of course, that's what the naive thing to do is. It's what elementary school students try to do all the time, 0 divided by 0. But it just, you can't do that. G, the solution set of this equation is all of Z. So there's no unique solution. So this should remind you of what we did for solvability of linear equations in modular arithmetic. So another example of this phenomenon is Zn with multiplication is a semigroup. And we spent a long time figuring out when we could solve equations like this in Zn. And it had to do with the whether this was coprime with the modulus, and if it wasn't, then you needed it to divide this and all that stuff. So this semigroups are just more complicated, which is why we like groups better than semigroups. Okay, so semigroups are the first thing we wanted to talk about. What is the next? Well, the next object is called a ring. And a ring is like a group, but instead of being able to do one thing, I can do two. So in a ring, I have not one but two operations, multiplication and addition. So it has two things I can do. And what do I want these things to satisfy? Well, I'm going to be more restrictive than a group. In fact, the operations have to satisfy, well, there's a first set of operations, rules, R1 through R5. And you'll notice that R1 through R4 are just the group axioms for the addition operation, right? The addition operation is closed. It takes elements of R back into R. It's associative. The addition operation has an identity element. And the addition operation, every element has an additive inverse, which is called minus x. We also insist that the addition operation is commutative. So it's not only a group, it's an abelian group. Okay. So we can add things in R, but we can also multiply them. So I have R6 and R7. So what do these conditions say? Well, again, this is saying it's a semigroup, right? It's the closure under multiplication. If I multiply two things in R, I get something in R. And it still satisfies the associativity property, which is sort of very important. So far I've just told you that it has a addition structure and it has a multiplication structure, but I need to tell you how they interact. Otherwise, this is just a set with two different things, and there's no interaction between the two. And the key ways in which they interact are the distributive properties. So if I multiply x times the addition of two things, I can distribute x on the left. And if I multiply z on the right, I distribute z on the right. And it's important that we have both of these because I'm not assuming that the semigroup has an identity element. So or rather that it's abelian, right? X times y may not equal y times x. So I may not be able to move this x to the other side of this parentheses. So I need to list both of these properties to be able to use both of them. So these are the axioms of a ring. And what are some examples of rings? Well, Z is a ring. This is sort of the most fundamental and basic example of a ring. It's something where when I add things, it acts like a group. So I have additive inverses. I know what it means to be minus of something. It's just minus of something. And Z has this distributive property, right? I know what it means to multiply things in Z as well. So, in fact, I would say that a ring, the definitions for a ring are sort of the most basic, is based on the integers. But of course, the integers isn't the only example of a ring, otherwise mathematicians wouldn't make this long definition. What are some other examples of rings? Well, it's the same as the other semigroup we talked about. M2, Mn, the group of the set of n by n matrices, is a ring. So why is this one a ring? Well, I know how to add matrices, right? I just do it coordinate-wise. So I look in the, right, A1, B1, C1, D1, plus A2, B2, C2, D2 is A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. So this is a group under addition, right? It has a zero element, which is just the zero matrix. Every matrix has an additive opposite, which is just I take its entries and I put all of the minus signs in front of all of these entries and put that here so that all of these things add up to zero. When I add two square matrices, I still get a square matrix. And it's certainly associative just because in each of the coordinates it's associative. So matrices are in a abelian group. Matrix multiplication is certainly a semigroup. That's what we just discussed. And if you've never done it, if you haven't taken 220, checking this distributive property for matrices is not difficult. It's just computational. So I'm not going to do that. But this is another very important example of a ring. And the important difference between this ring and this ring is that elements of this ring don't commute when you multiply them, right? That's what I was saying when I was discussing why we need to list both of these operations. When I multiply A times B, it's not the same thing as B times A. So nowhere in my axioms for a ring do I insist that multiplication is commutative. I only insist that addition is commutative. Okay. What's another example of a ring? So R of x with square brackets on x denotes the set of polynomials in the variable x with real coefficients. Right, so for instance, x squared minus 2x plus 1/2 is an element of R of x. This is a polynomial whose variable is x, and all the coefficients here, the coefficient is implicitly 1, 2, pi x cubed minus square root of 2x plus 1 is also an example of a polynomial in R of x. And what is a polynomial is just this formal combination, this formal sum of x squared terms, x cubed terms. You can go arbitrarily large degree of polynomial, but there has to be a maximal degree. The degree, it's not some infinite sum like sine and cosine, not some power series. It's just the polynomials. So the polynomials are a ring. Right, I can certainly add two polynomials and get a polynomial. I can just factor out this x squared term, and so I get that the coefficients are going to be real numbers again. And I can multiply them as well, right, using the distributive property. Right, so like x minus 2 times x squared plus 3x minus 1 is, well, what's the x squared term? It's x cubed. Let's find all the the x cubed term is just, there's one x cubed. Let's find the x squared terms. Here I get a plus 3x squared minus 2x squared, so plus x squared. What's the x terms? Minus 6 minus x is minus 7x. And the constant term is 2. So whenever you give me two polynomials, when I multiply them, I still have a polynomial. So the set of polynomials is another example of a ring. Again, it's very easy to see that adding two polynomials gives me a polynomial. Addition is associative. This is just usual associativity. The zero polynomial is just the zero. Zero is definitely an element of R of x. It's just all of my coefficients are 0. The opposite of a polynomial, I just take minus in front of each of these terms. So I just put a minus sign in front with parentheses and then distribute the minus sign, and I get the opposite polynomial. And addition is certainly abelian. This one also has its multiplication abelian. So group multiplication, here, the ring multiplication. Of course, when I multiply two polynomials, I get a polynomial. When the multiplication is associative, and I have this distributive property. So in this case, the set of invertible elements is very small. It's just the set of constant polynomials, the non-zero constant polynomials. Those are the only ones that are invertible inside of this ring. Everything else is not invertible. Hopefully, towards the end of the course, we'll be able to talk more extensively about polynomials and polynomial rings, and sort of talk about how R of x looks a lot like z of z, and how our analysis about divisibility properties in the Euclidean algorithm for z can carry over to this polynomial ring. Okay, so that's what a ring is, and we've got 2 more definitions, I think. Yep. So our next definition is that of a field. And this one will be the shortest one for our discussion. So a field is a ring, but I want a couple more things to happen. I want the multiplication to look more like multiplication on the real numbers, or multiplication on the rational numbers. I want there to be an element which acts like the identity element in the multiplication, and I want to be able to divide by things, as long as they're not 0. So 0 should be the only element that's not invertible. And 0 is always going to be invertible, not invertible, by the distributive property. Maybe I can give that as a homework exercise next week. Right, so what are examples of fields? So the examples that I gave before of rings, the rings discussed this far, so we discussed, are not fields. So, right, the integers is not a field because 2 doesn't have a multiplicative inverse. Not every matrix is invertible, so this ring of matrices is not a field. It's also not a field because it doesn't commute, right? Oops, I needed this additional axiom. 3 additional axioms. xy equals yx for every x and y in R. So I need my ring to be abelian for it to be a field, and this one's not abelian. This one's not a field for the same reason that z is not a field, because I can't divide by polynomials and still be a polynomial. Now, you can define the field of rational functions, but that's not what we're going to be doing here. Okay, so examples of fields. R, Q, and the complex numbers are all fields. ZP, or Zn as a field, is always a ring. But a field if and only if n is prime. So when we were discussing Zn earlier in the course, we talked about how you can add, multiply, but in general you can only divide if a number is coprime with n. So the only way in which every non-zero element is coprime with n is if n is prime. Otherwise, the field axioms fail. Let's do one more example that sort of hints at a field called, or a subject called algebraic number theory. So a lot of algebraic number theory cares about fields and what are called field extensions. So here's an example of a field extension. When I take Q and I tack on the square root of 2. So this is the set of things A plus B times the square root of 2, where A and B are elements of the rational numbers. So let's just check all of the field axioms, right? So I need to first check the ring axioms because the field needs to be a ring. Well, when I add two elements like this, I get that I can just use the distributive property of the real numbers and group it like this. So this belongs to the rationals, this belongs to the rationals. So this sum can be expressed in this way. So what does this show? This shows closure under addition. R2 is associativity, and I can just rely on the associativity property of the real numbers here, right? If these are actually real numbers as well, so when I add three of them, it doesn't matter the way that I group them because I'm just adding real numbers. 0 is an element of R because I can just take A and B both to be equal to 0, and then I get just the number 0. So 0 is definitely an element of Q adjoin the square root of 2. And 5 or minus signs, sorry, R4. R4 is opposites. So what do? Minus A plus B times the square root of 2. It's clear what needs to be done, right? It's A minus minus B times the square root of 2. And this certainly still belongs to my set, Q adjoin the square root of 2. The abelianness of addition just comes from the fact that when I add two things in the real numbers, they commute. So if I add A1 plus A2, this is the same as A2 plus A1. Right? It doesn't matter the order in which I add things. So the addition stuff, everything is fine. Now let's check multiplication. And this is where the extra field axioms come into play. So I need to check that when I multiply two such things, I'm still in Q adjoin the square root of 2. And indeed, if I do this, it's just going to be 2 b1 b2. Right, because the square root of 2 squared is 2, so this is, when I multiply these together, I get 2 b1 b2, and then the square root of 2 term is going to be a1 b2 plus a2 b1 times the square root of 2. So this is a rational number, this is a rational number, so this is part of Q adjoin the square root of 2. So multiplying things keeps me inside Q adjoin the square root of 2. What else do I need to check? I need to check associativity. This is just going to follow from the associativity of real numbers, right? These are actually real numbers, so it doesn't matter how I group my multiplication. I get the distributive property again for free because I'm just multiplying real numbers, right? If I multiply this real number times the sum of these two, it's the same thing as doing this. The real numbers are distributive, so I don't have to worry there. So the last thing I need to check is the field axioms here. Again, this is a subset of the real numbers, and I'm using the real numbers multiplication. So if I multiply x times y, it's the same thing as y times x, right? It's not like matrices where things don't commute when you multiply them. This is just a collection of real numbers, so the order in which I multiply them doesn't matter. I need to check that 1, the identity element for real number multiplication, is part of Q adjoin the square root of 2. In addition, looking at this, I can see that if I take a equals 1, which 1 is a rational number, and b equals 0, 0 is a rational number, I get 1. So 1 belongs to R. And finally, I need to check that every element has its inverse, and this is the last computation to check for q adjoining the square root of 2. So I need to check that 1 over a plus b times the square root of 2 belongs to q adjoining the square root of 2. And this is something maybe you've all done before, hopefully. How do I do this? Well, I complete the square and get a minus b times the square root of 2 in the numerator. And this is a squared minus 2b squared, which is a over a squared minus 2b squared plus minus b over a squared minus 2b squared times the square root of 2. Now what's the danger? The danger is that this element a squared minus 2b squared is equal to 0, right? That's the only way that this can happen. But then, for this to happen, I would need a to equal b times the square root of, plus or minus b times the square root of 2. So if b were not equal to 0, I can't have both a and b be rational numbers, because if b is a rational number, b times the square root of 2 is not a rational number. So I'm using some more complex ideas here. We're not going to come back to these proofs in this course. I'm just sort of, the book goes over this, sort of skims over it, so I'm trying to do the same. So since a and b are both rational numbers, the only way to satisfy this is for a to be equal to, a and b to both be equal to 0. Which means the only number I can't divide by is 0, which is what I want. So this is the last example of a field I want to go over. Doing field extensions like this has a lot of interesting applications and ideas surrounding it. So if you're interested in this, look up or take a course in algebraic number 3. Okay. So this is a field. Again, to recap, a field is just a ring with these additional axioms that make it have multiplicative inverses, basically. It has to have a multiplicative identity and a multiplicative inverse, and it needs to be abelian, the multiplication. Okay, so what's our last definition in this section? Our last definition is what a vector space is. And a vector space is just like your usual definition of a vector space, but instead of being able to multiply by things in the real numbers, it's now a vector space over an arbitrary field F. So what can you do with the vector space? Well, you can add vectors. So I need V to have an addition that makes it an abelian group, right? I need to be able to add things in my vector space. I need to have a 0 vector, and so on and so forth. I can't multiply things in vectors in the vector space and get another vector. What makes it a vector space in relation to the field is that I have some notion of scalar multiplication. Right? So usually we just write scalar multiplication as lambda times v, where lambda is an element of the field and v is an element of the vector space. So if you give me a number in my field and a vector in my vector space, lambda v represents the vector v scaled by the number lambda. And I just need to satisfy these axioms. So v1 is just that the output of this function sigma is in v, so I skipped it here. So, but v1 is just closure under scalar multiplication. Lambda times v is an element. Lambda times little v is an element of capital V. What are the other vector space axioms? Well, I need some sort of associativity property of the multiplication, right? If I multiply by lambda times mu, it's the same thing as multiplying by lambda multiplying this vector, mu times v, by lambda. I need the identity, the unit element of my field, right? 1, which is the element of my field, just to multiply my vector by 1, right? This is like if I think about vectors in coordinates, and this is sort of a useful way to get some intuition about vectors, but you can't always write down coordinates for vector spaces. But if I think about a vector space like Rk, 1 times a vector, I just distribute the 1 into each of the coordinates of the vector. Lambda mu in F and V, this is one of the distributive properties. So if I'm multiplying my vector v by the sum of 2 field elements, I can multiply the vector by each of those field elements and then add the results instead. So this is one of the distributive properties, and the other one is that, well, now I have just 1 field element but 2 vectors. So if I'm adding 2 vectors and then multiplying by the field element, it's the same as multiplying each of the vectors by the field elements and then adding the results together. So vector spaces, I would say, are the most useful objects in mathematics. Maybe that's a bold thing to say, but there's a reason that we have a whole course dedicated to linear algebra. You know, once you get past Calc 1, and you quickly realize that you need to use vectors instead of just numbers to keep track of things happening in multiple dimensions. So a vector space over a field is a generalization of all of those notions to work in an arbitrary field. So I'm going to go over 2 examples of vector spaces. One is just Rk. This is just everything you learned in Math 220. Right? It's very easy to confirm all of these properties for Rk. So an element of Rk is just v1 up through vk, where each of these are real numbers. And then I just add coordinate-wise. When I multiply, I distribute the vector into each of the coordinates. It's a very important vector space to get familiar with and prove things about. Here's another interesting vector space, the space of polynomials. So why is this a vector space? Well, I can multiply a polynomial by a real number, and it's very easy to check all of these axioms for polynomials, right? If I add 2 polynomials and then multiply by a real number, I can distribute the real number into the sum. So this is an example of an infinite dimensional vector space. And this is sort of where we start to diverge away from algebra and into the realm of analysis. So infinite dimensional vector spaces presents lots of problems when you try to generalize things like norms or dot products. Are huge problems here. And sort of tackling what to do when trying to define the norm of a polynomial, for instance, is of some sort of the birth of a field called functional analysis. And again, we're not going to be talking about functional analysis here. I just wanted to give you sort of an indication that, so maybe a justification why vector spaces are the most useful definition. I can't think of a mathematical field even a scientific field that doesn't in some way use matrices and vector spaces. These are sort of the most important objects to understand in mathematics. Most people care about vector spaces over R, but if you stick around mathematics enough, you'll find vector spaces over Q, vector spaces over field extensions of Q, like Q adjoin the square root of 2, and vector spaces over finite fields like ZP are also very interesting to study. So I think that's going to wrap it up for today's lecture. I know we didn't prove much today, and I know it was a lot of definitions to try to absorb. I tried to give as many examples as I could. This is just sort of a pause in our discussion of groups. We're going to be focusing on groups from now on for the rest of the semester. And really, any questions on the final or on the homework about these topics will just be about giving examples or definitions related to rings, fields, vector spaces, and semigroups. Okay, so we're just going to do one lecture on section 4.4, and next time we will talk about, we'll jump into chapter 5. Thanks, and I will talk to you soon.